In your reading, you looked at mathematical methods to calculate the center of mass of simple objects. I want to explore a couple experimental methods as well. Here we have three simple objects. They have high degrees of symmetry and they have uniform densities. The centers of mass of these objects are at their geometric centers. Here's another highly symmetric object, a racquetball. The center of mass of this object is also at its geometric center, which is weird because there is no actual mass there at all. Symmetry is a powerful tool in finding the center of mass of an object. For objects with uniform density, the center of mass will always be on any existing line of symmetry. One way to find the center of mass of an object experimentally is to observe it as you attempt to tip it over. Consider a uniform block on a table. The bottom of the block is called the base. By symmetry, the center of mass of this block is here in the geometric center. This green line is a reference line for the center of mass. Basically, it's a line drawn perpendicular to the base which passes through the center of mass. The angle between this reference line and the normal line from the table is how we measure tip. At small tip angles, the object will return to its original base. At high tip angles, the object will switch bases, or fall over. At a certain critical angle, the object will try to balance on the corner between the two bases. This is the angle where the center of mass is directly over the corner. By geometry, you can see that the critical angle can be measured in these three places. If we zoom in, we can see how to measure the critical angle. We can draw a right triangle inside the object, using the half of the base length as the opposite side, and using the height of the center of mass above the base as the adjacent side. Let's look at some real objects. Our uniform rectangular block is not very exciting. As we hold it at the critical angle and draw the normal line and the center of mass line, we see that they intersect at the geometric center of the block. Boring. If I reorient the block and try to tip it over from this new base, the same thing happens. Here's a different block. Look where it balances. Notice that the intersection of the center of mass line and the normal line is much lower on this block, resulting in a greater critical angle. What's causing this? The block is now uniform. There are all kinds of holes in it. The bottom of the block is more massive than the top, thus lowering the center of mass to a point well below the geometric center. Here's a bowling pin. Look at that narrow base. Look at that high center of mass. Remember, its job is to fall over, and it is built accordingly. Look how small that critical angle is. This is an Erlenmeyer flask. Its job is to not tip over. It has a huge base. All the mass is in the bottom. Check out that critical angle. It's almost impossible to knock this thing over on accident. This is a 12-ounce claw hammer. It is interesting because it does not have uniform density. The head is way more dense than the neck. The yellow tape is wrapped around the geometric center of the hammer. The white tape is wrapped around the center of mass. The hammer will not balance on the yellow tape, but easily balances on the white tape. This is a toy plastic bird. It is molded so that the center of mass is at its beak. Notice how the wings sweep forward, but not much in front of the beak. Certainly not enough to counterbalance the tail. They cheated. There are little metal plates in the fronts of the wings. Lastly, what happens if we have an object that we can't try to balance on a table? Here's a random piece of cardboard that I want to find the center of mass of. If I pinch it tight, I can hold it up at any angle I want. However, if I pinch it loosely, it will swing down until its center of mass is at as low a potential as it can get. If I also pinch a plumb bob along with the object, I can be sure that the center of mass is somewhere along that plumb line. If I rotate the object through an arbitrary angle and do it again, I'll get an intersection of the two plumb lines. This must be the center of mass. A third trial is unnecessary, but I wanted to do it to demonstrate that any orientation will give the same result. You now have 3 experimental tools to find centers of mass in the laboratory.